Lab's three purpose was to use a computational model to determine the unknown mass of a black hole and model the motion of both the planet and the ship around it. The lab was divided into two parts. One consisted of writing a code on GlowScript in order to determine the mass of a black hole using Newton's second law and the universal law of gravitation. Part 2 of the lab consisted of determining the initial speed needed to circumvent the black hole once launched off an orbiting planet, which was also done using the universal law of gravitation. In part 1, the mass of the black hole was determined to be 1.713 times 10 to the 34th kilograms. Using this determined mass and pre-designated values, the initial velocity needed in part 2 was determined to be negative 5 times 10 to the 7th meters per second in the x direction, 1.6 times 10 to the 6th meters per second in the y direction, and 0 meters per second in the z direction. In part 1 of the experiment, the orbit of a star was modeled in GlowScript in order to determine the mass of the black hole at the center. Using fundamental laws of physics, a computational loop was created to calculate the net force at every position of the star. The system is the star, and the surroundings include everything else. Positions of the star were predetermined by a seed generator using my email. The mass was also pre-given, and so was delta t, which was 1 day, but in seconds is 86,000 seconds. Code additions start in line 163. This first small chunk of code calculates the initial and final momentum using the definition of momentum mass times velocity. The second chunk of code finds delta v and delta p using final minus initial. Line 172 approximates dp dt to be delta p over delta t. And we know that dp dt is equal to F net from Newton's second law. dp dt parallel is then determined using the formula d magnitude of p over dt times p hat equals delta p over delta t parallel. So we know that dp dt is the sum of dp dt parallel and dp dt perpendicular. We can subtract dp dt parallel from dp dt to get the perpendicular component. The last part of the calculation rearranges the equation for universal law of gravitation in order to find the radius and then eventually find the mass of the black hole. Arrows were then coded in to represent the different force components, and the final output was yielded to be an average mass of 1.71 times 10 to the 34th kilograms. In part 2 of the experiment, the orbit of a planet around the black hole was modeled to determine the initial velocity a ship would need in order to escape both the planet and the black hole if its engine failed right after takeoff. Once the motion was modeled, the initial velocity was found through trial and error. In half of the code, the system was the planet, and the other half is the ship. The surroundings include everything else respectively. The code from part 2 takes the value from the first code to calculate the new values. The simulation runtime is set to be 1 hour. The values for initial speed in the yellow box were determined from trial and error based upon the results from the code on the right. To determine the initial velocity, first, the forces on both the planet and the ship had to be found. Using the law of universal gravitation and a direction vector found from the differences in the positions, the net force on the planet and on the ship were both found. From then, the task was simply to input the net force into the velocity update formula, and then that into the position update formula in both the planet and the ship's case. Then, through trial and error using that code, the initial velocities were found to be negative 5 times 10 to the 7th in the x direction and 1.9 times 10 to the 6th in the y direction. Here's the visual of the ship escaping the black hole's orbit without hitting the planet or the black hole. What does it mean? Mathematically, there is no difference between net force and the rate of change of momentum. This is true because Newton's second law states that they are equal. A simpler version of Newton's second law is force equals mass times acceleration, and since acceleration is the rate of change of velocity and it's multiplied by the mass, it ends up being the same product as the rate of change of momentum. Where the rate of change of momentum truly differs from the net force is when it comes to observability. Without any specific tools, force is not observable. Momentum, on the other hand, is very easy as you can measure mass, time, and position. What if? If an orbit around the black hole is wanted, an initial velocity of negative 9 times 10 to the 5th meters per second in the x direction, 1.08 times 10 to the 7th meters per second in the y direction, and 0 meters per second in the z direction is needed. And this was found through trial and error.